Get started. Looks like we have a good crowd here today, so welcome everyone, and thank you all very much for joining in on the first webinar as part of the Discovery Farms virtual conference series. The theme for this series is keeping up with your conservation goals through change and challenge, and it's being brought to you by the Discovery Farms program in Wisconsin and Minnesota. So it looks a little bit different as our traditional yearly conference, as some of you might have attended in the past. But we're excited this year to be able to partner and bring the conference across state lines in Wisconsin and Minnesota and welcome a virtual audience from near and far. We have a really exciting lineup of speakers for you all. The Discovery Farms program, for those of you who might not be as familiar, is a farmer-led research and outreach program focused on the relationship between agriculture and water quality. And here in Wisconsin, we're a part of the UW-Madison Division of Extension. And in Minnesota, they're a part of the Minnesota Agriculture Water Resources Center. So thank you for being here with us today. A couple of housekeeping things as we go throughout this webinar series. We did apply for CCA credits and got those approved. So what I'm going to do right now is I'm going to quickly share this QR code on my screen. Can everyone see that? So if you're hoping to get some CEUs today, feel free to scan that code in. But also if you don't have the app to collect that code, you can also type your name and CCA number in the chat. And this is being recorded, so we'll be able to record that and get you your credits. As we go throughout the webinar today, we're going to use the chat feature. So as you have questions, feel free to type those into the chat box. And Walter and Didi are going to save time, a good chunk of time at the end for discussion. So we'll get to those questions, definitely. So I don't want to take up any more time with the introduction because we have some very exciting speakers with us today for the talk titled Mitigating Climate Change Through the Soil Carbon Sponge. So all the way from Australia at 5 a.m. in the morning, we have Walter Jehne joining us, and he is an internationally known microbiologist and the director of Regenerate Earth. And we also have Didi Pershouse from Vermont, who is an author and the founder of the Land and Leadership Initiative. So thank you, Walter and Didi, and welcome. And I'm going to turn the mic over to you. And it looks like we still have some people joining, so we'll continue to admit people.
Right. Well, look, thank you very much, Erica, and welcome everyone from Australia. And yes, it's 5 o'clock in the morning here, but again, perfect every day, and yeah, enjoy. But look, what we wanted to talk about was, yes, the bigger challenge and the change that has to come from that. And of course, the challenge is really fundamental because, as we all know, we're experiencing it, things are changing. Climate is really changing. It's now starting to bite. We in Australia here have had extreme, well, it's summer again here now, but extreme hot weather, 40, 50 degrees centigrade, but then really serious impacts, things like wildfires, where literally last summer we lost half of our whole forest. It will regenerate, but we're really looking at these fire extremes. And so I think we've got this fundamental challenge right across all parts of agriculture, all countries. How do we actually address these hydrological climate extremes? And it's much, much more than that sort of passive CO2 increase and the greenhouse effect, because these climate extremes are, yes, hydrological, and they're happening now, way before what we would formerly saw as the scenarios, the prescriptions. And so the real challenge is, how do we address those? You know, how do we actually at the grassroots, community level, individual farmer level, address these imperatives? And of course, it's all about building resilience in our ecosystems. You know, how do we actually take our existing landscapes, farms, agriculture, forests, and how do we build resilience in those systems so they can avoid and buffer these changes. It applies also, of course, in our social systems, because as we're seeing now with the COVID virus, we're basically saying, okay, not that COVID is directly related to climate change, but basically we're now more and more vulnerable to these, again, extremes. So what is it that we can do? What is it that we must do to limit those and avoid their impacts? And what we're going to talk about today is really, okay, how does nature address these problems? You know, what is it that nature did to create resilient, buffered, productive biosystems? And what can we do to restore those? And it all comes around to this actually very wonderful and natural, simple solution that's available to all of us. And it all revolves around regenerating the Earth's soil carbon sponge. And it's a concept that Didi and I have been, in a sense, communicating for quite some time. But really, it's what nature did. See, it took CO2 from the air through plant photosynthesis, biosequestered them in the soil, created the soil carbon sponge, and in that process was able to basically build the hydrology of the planet, build the biosystems, you know, the forests, the vegetation, the animals, all those ecosystems we depend on, but also through that hydrology, naturally cool the climate and stabilize the climate. And really, that's what we want to talk about, because we can use those same systems to now practically all over the planet build resilient biosystems, cool the planet, and actually stabilize what is otherwise going to be some pretty serious impacts. So that's the context of what webinar is about. What we want to do is talk about then some of the science and the details and the practice, but most of the time we want to then open this thing up for interactive discussion with you, because it's how does it apply in Wisconsin, how does it apply in your farming system, and how do we as basic grassroots communities look at these systems and manage them. We've got very, very innovative farmers all over the world, and they're basically leading in actually designing and implementing these strategies. And really there'll be questions from your audience to say, okay, well, what do we do? How do we do it? What are other people doing? And we're all learning, and we're actually refining solutions through that interactive process. So that's a big part of the discussion, because it's the Q&A, the questions, but then what are the experiences, the case studies, how do we apply those? So that's the big picture. Bit of an introduction as far as who I am. I'm a soil microbiologist. I'm a research scientist. I worked for a long time with our leading research institution in Australia. I've also spent a lot of time in government looking at where do we actually, or how do we actually communicate and implement these innovations? So what's limiting innovative change, and how do we catalyze that? But for the last 15 years, I've retired and now basically working with NGOs, farmer groups to look at, okay, how do we actually do the thing on the ground, catalyzing change? Initially, that was basically with farmers mainly in Australia, but progressively it's got bigger and bigger. And so now we're working with other groups all over the world, India, New Zealand, of course, America, EU. And it's basically a very, very large movement, all looking at, yes, what are the imperatives, the pressures for change, but then where are these ecological solutions? And then Didi is also on this. Now, Didi, do you want to introduce yourself at the moment and sort of say a few words, or do you want to do that later?
Sure. Well, I thought I might jump in and show a few slides first that I think will give people a bit more of a picture of what you're talking about as you get into the details, if that works for you.
Yes, perfect.
Great. Okay, so I'm going to go ahead. I'm Didi Pershouse. been working with Walter since I think 2015. We met at a water conference at Tufts University, and I was showing a demonstration of the soil sponge, but didn't have the language, and he was talking about it, and we ran up to each other afterwards in great excitement, and have been friends and colleagues ever since, and kind of spreading the word, as he said. And this has involved several trips around the country here. We do an annual conference in Vermont that we'll see if we can get one online going soon. We'll be teaching a class together quite shortly, an online course, as we've done before. And I'm also the author of 2 books. One is called The Ecology of Care, and the other one is called Understanding Soil Health and Watershed Function, which is a free download you can find at landandleadership.org. I'll share that later. So I'm going to go ahead and just share. Let's see, hang on one second. It's always a little bit of a funny thing to get going here. Okay. Great. Okay. All right. So what makes a sponge a sponge? We're using this funny term, soil sponge or soil carbon sponge. And if you think about a kitchen sponge, a sponge wouldn't be a sponge if it fell apart whenever water hit it, right? If it fell apart in your sink, or if a little breeze went through the room or wind blew through and it fell apart, that also would be a problem. So one aspect of a sponge is the structural integrity of it. And that is true in a soil sponge as well. The other thing that obviously makes a sponge is its capacity to soak up water and to hold that water as you know, in a kitchen sponge sense, as you move it from place to place. But for a soil sponge, you want it to soak up that water and keep it at the root zone for plants for later use, and to have it filter down through the soil and fill in our wells and our aquifers, but also to go down and slowly refill rivers and streams and lakes from the sides and bottoms, not so much from the top. We're not looking for more runoff. So I often, this is how Walter and I met with some students of mine. We're showing this demonstration at the conference. And what I do to talk about the soil sponge is to thinking about flour as a stand-in for the sand, silt, and clay, the mineral particle of soil. And that when flour is just by itself and doesn't have any biology in it, if you blow on the plate of flour, like if a wind came across a landscape, all of those mineral particles blow away. And we see that actually, we see that in you know, we've got soil coming across from the Sahara to other continents. So, but also what happens when it rains on a soil sponge. So here's a demo you can do with your friends at dinner parties or at conferences or with kindergartners or even speaking at the UN. We've done this all over the place. If it rains on soil that doesn't have any structural integrity, that is not a sponge, then the water runs off. So we get a lot of runoff. We get erosion, water erosion. We get soil in our rivers and streams and lakes. And of course, that's carrying with it any nutrients, et cetera, chemicals that are on or in the soil. So we're seeing flooding here, but we're also seeing drought. So if you lift up that top layer, anyone who's done any baking knows that the flour underneath there is dry. And if you put that out into the sun, then you're going to get a crust on top that's going to make it harder for the next rainfall to infiltrate. And we see this in soils all the time, that each rain event that happens moves those tinier particles, those small mineral particles sideways, and they start filling in the open pores so that you get crusting and sealing of soils. So, lack of a soil sponge is a major factor in our algal blooms that we're seeing, in flooding, in drought, which are really two sides of the same issue. It's a major factor in the length of the green season, how long plants can actually grow. And it's, as Walter will talk about, it's a major factor in actually the health of the crops and their resilience, and by extension, the health of the animals and humans that eat those crops. So what do you need to do to change flour into bread? Well, you have to add biology, right? And in soil's case, that biology comes along in the form of plant roots and their exudates that feed the biology in the soil, and all of those glycoproteins and slimes and glues stick those mineral particles together. And as they stick together, there are spaces that are created around them. And then as life moves through there, so as plant roots and fungal hyphae and worms and other life in the soil moves through, you suddenly get a porous structure. And you'll see that as you've seen in healthy soils, perhaps, that the function of something that has this structure is completely different now. So it's soaking up the rain that falls. There's no flooding. It's going down to the root zone for the plants. And there is no erosion happening. There's no mudslides. There's protection now against drought. That water's being held in a place where no one can tax you for it, for irrigation money. It's yours. And it's there for all the life in the soil. And as you'll see, when the water does start coming out and filling in the lakes and streams, et cetera, it is filtered. Okay. Another way of looking at this, and I bet many of you have seen this Slake test that Ray Archuleta has popularized to show the structural integrity. You can put a clod of healthy soil into water, and for many, many hours, even overnight, it will maintain its structural integrity due to those biological glues that are holding things together, whereas unhealthy soil will tend to fall apart as soon as you put it in the water. And here's another one that you may have seen around that the NRCS soil health team has popularized, is a rainfall simulator. And you'll see maybe slightly covered over by your participants, but you can usually move that window aside. You'll see that the place where no soil health principles are being used there, that as we've put like 4 inches of rain on this pan that's open on the bottom, none of that water is getting through to the plant roots, and it's all running off and taking soil with it on the far right. Whereas the more and more soil health principles you put into effect, which is living roots in the ground, diversity, integrating animals, reducing biocides, and very importantly, reducing tillage or eliminating tillage, you see that suddenly you've got all the water going through to the plant roots. It's clear and clean, and there's no runoff on the far left. This is a close-up picture of the soil sponge taken by our friend and colleague Phil Lee at Regenerate Earth. And here you can see the fungal hyphae and the glues sticking those mineral particles together. And you can see the spaces that are created as those mineral particles get held in that structure. And Walter likes to talk about that space as a cathedral, and I love this picture as a sacred space that you can imagine the water actually going right down through. To me, this image is kind of a human scale image of the soil sponge, and there's life in there, right? So I have an article that came out this morning on Medium on the Regenerative Economy Collaborative that's called Other Species Are Essential Workers whose economies enfold our own. And that's making the point that the work of other species really behind everything that we need for our human economies. So, but humans can't build this infrastructure, right, of the soil sponge. It requires this diverse biological workforce. And I love this quote by another colleague of ours, Peter Donovan at the Soil Carbon Coalition. The issue is that over vast areas of the world, the biosphere, or life, is not doing enough work. With livestock confined and crop monocultures dependent on fossil energy to maintain them, too many of the animals are in prison, too many of the plants are on welfare, and too many of the microbes are dead. So what do we do to give this biological workforce good working conditions? Well, we need acceptance, welcome, and respect for a diverse workforce. They need food and water year round, and that comes from having a continual cover cropping that is feeding the soil life underground. They need protection from sun, wind, and rain, so that's plants and a mulch layer. They need protection from toxic chemicals, just like any other workforce. And they need to be self-organizing labor that is trusted to make its own adaptive decisions. So we need to let this biological workforce build the sponge, not disturb it with plows, et cetera, not poison it, not leave it out in the wind and cold and heat. And really, as we're learning to do in so many parts of life, accept and welcome a diverse workforce. So thank you for that. And I'm going to turn it over to Walter. Let's see, I think, well, yeah, we've got two more here. Which side of the fence do you want to live on? Here's a side that's got a healthy soil sponge and one that doesn't. And if you want to learn or teach more, this is actually a facilitator's manual. This is the website that you can go to, and that will be where Walter's and my course will be listed probably sometime in the next week or so. Okay.
Right, wonderful. Thank you, Didi. And look, this is very important because that gives you the concept of the sponge, you know, that three-dimensional matrix of mineral particles, organic particles. But the really, as Didi mentioned, the whole key thing is the voids, the spaces, the nothingness in that sponge, because they're the cathedrals, they're the open air, but that's where, in a sense, that soil can infiltrate, retain, make available water, allow plants to grow, allow microbes to grow. And it's really, that's our point of agency. It's the only point of agency we have as humans in terms of agriculture, and how do we actually build healthy soils, and through that build the hydrology and the nutrition of those biosystems. What I'd like to do now, though, is we've got that concept of a sponge, then let's go back now and say, well, look, what's it got to do with climate change? And how do we use that sponge as actually our tool and solution in climate change? Because as we've said at the beginning, it's these hydrological extremes that are really dangerously impacting communities: flooding, droughts, fires, wildfires, etc. And really, what is it that we can do? Now, for the last 50 years, we've obviously sort of recognized climate change. It started 50 years ago, Charles Keeling sort of putting that data up to say, look, here was CO2 going up abnormally. And of course it is. And of course, we very much focused on the symptom, the CO2 increase, to say, hey, we've got this increase, we've got to address this symptom. But actually, much more importantly, we've got to address the cause. What is causing that CO2 to go up? And that's our management of our soils, our use of fossil fuels, oxidizing or burning that carbon from the soils, from fossil fuels, to add to that symptom. And of course, CO2 is a greenhouse gas, and it does contribute to, of course, warming. There's no question, again, on the science. But we've got to look at it in the bigger context, because the CO2 component of the greenhouse effect, that gas effect, represents some 4% of the Earth's heat dynamics. 95% of the heat dynamics of the blue planet is in fact governed by water. And this is really a basic, physiological or physical reality. And basically, we're asking the question, can we actually, by managing the sponge, enhance our management of the hydrology, restore the management of the hydrology, so we can use that to buffer and mitigate climate change, that we can actually naturally and safely cool the planet. And if we look at the planet then in that bigger context and the challenge that we've got, obviously we've got a planet and it's the sun that's bringing energy continually into that planet. And on average, some 342 watts per square meter of solar energy is reaching the upper atmosphere continually. And of course, to have a balanced temperature, that planet has to release and re-radiate 342 watts of energy back out to space. But what we've done is we've retained extra of that re-radiated solar energy, so that we're now keeping an extra 3 watts per square meter, roughly, of energy in the atmosphere, warming the planet. And that's, in a sense, global warming. But the message that is important to take here is that, yeah, we're heating the planet 3 watts out of 342 watts total coming in. So that's less than 1%. So the challenge we've got, and this is all about challenge and change, the challenge is, can we rebalance the Earth's heat dynamic by that 1% to re-stabilize a safe climate and allow the future to keep on going? Because if not, we are in serious troubles. And of course, if we do that, we ask the question, well, how did nature regulate that climate? And when we go back into nature, we sort of say, yes, nature did this extremely efficiently by regenerating the Earth's soil carbon sponge, or in fact, generating it in the first place. If we go back 420 million years, there was just ocean and rock on this planet. There wasn't life, there wasn't soil. And nature, of course, used these microorganisms, the fungi, the algae, the lichens, and just as Didi had explained with the flower, nature used those microorganisms to solubilize the rock, glue it together, make that organic matrix of mineral particles and organic matter, the sponge. And of course, in doing so, it was then able to retain water and of course, progressively build healthier soils. Those soils in turn enabled vegetation to colonize the land surface. And so very rapidly in the Carboniferous, the whole of the Earth's land surface was colonized by plants. And of course, it built a completely new hydrology because of that sponge. And in a sense, it's that hydrology of the sponge that now has regulated the Earth's climate for these last hundreds of millions of years. And it's that process that we can also use now to safely, naturally cool the planet. So let's look at some of those hydrological processes that can be so critical in cooling. But most importantly, these are processes that we can influence, we can manage to safely bring back a safe climate. And if we've got a sponge, if we've got water in our soil, and if we've got vegetation, then every child already knows that no, we can actually have transpiration and evaporation from that soil via those trees, via that vegetation, taking water from the sponge up through the trees and releasing it into the atmosphere. And as it does that, it has to turn that water from a liquid into a gas. It has to go from liquid water to water vapor. And to do that, it takes an enormous amount of energy to convert that liquid to gas, some 590 calories per gram of water, per cubic centimeter of water, is the energy it takes, for example, when we have to boil a billy or make tea, turn liquid to gas. And that's actually a transfer of heat from the Earth's surface back up into the atmosphere. And of course, that transfer of heat cools the surface enormously. And if we look at it at a global level, 24% of the incident solar radiation coming in from the sun is in fact naturally taken from the surface into the atmosphere through this transpiration and evaporation stream. So again, it's an enormously powerful process. And so if we just increase the transpiration, increase the vegetation or the green growth, transpiring this water, taking this heat from the surface back into the air, we can safely and naturally cool the planet. In fact, mathematically, some 4% increase in transpiration, a 4% increase in green growth would offset that 1% warming effect that we've had through global warming. And we can then ask ourselves, well, is that possible? And of course it is, because basically we can extend the area, the longevity of green growth through our farming practices, and in that way cool the planet. But it goes on, you see, because once that water is in the air, then it has a very profound effect as a gas in actually absorbing solar energy and contributing 80% of the greenhouse gas effect. Okay, and so when that water is in the air as water vapor, it's actually warming the planet. But if it coalesces and forms clouds, cloud microdroplets, and these form high density, high reflective clouds, then again, that water in the air is an enormous cooling effect because it immediately reflects incident solar radiation back out to space and actually enables us to cool the planet below that cloud surface. And you know, when a cloud comes over, then it's cooler. And of course, we have to put on a jumper or coat, and it can cool the atmosphere rapidly. And again, by increasing the nucleation or the coalescence of these clouds, the dense high cloud formation, we can basically cool the land surface. 33% of the incident solar radiation from the sun is actually reflected naturally back out to space through clouds. Over 50% of the Earth's surface at any time is naturally covered by clouds. So again, we can influence that, but only if we have the sponge, only if we have this transpiration, and only if we enhance the formation of these clouds. And of course, we can do that, again, biologically, naturally, because to form these clouds, these water droplets, they have to nucleate around or coalesce around aerosols and mineral particles and also bacteria. And these bacteria are coming again from the forest, and they're acting as precipitation nuclei. And of course, if we have more forest, more vegetation, we're actually helping this cloud formation. The next step in the process, of course, is if we have vegetation on the land surface, then basically we're keeping that surface protected from incident solar radiation. We're keeping it much, much cooler. And of course, that cooler surface will re-radiate much less heat back out to space because it's basically, kept cooler and it's not re-radiating as much heat. And again, it's that re-radiation of the heat that is the principal factor driving the greenhouse effect. So what we've talked about now here are three processes where we can naturally, safely cool the planet, and we can cool that planet easily, that 3 watts per square meter that we've warmed the atmosphere. And in a sense, it's realizing these are then the tools that we have through land management to actually return the climate back to a stable, healthy state. of course, we've got to draw down carbon into the sponge to do that, but it's actually the hydrology that we're restoring, which is a powerful effect in cooling the planet, not just the CO2 in the air. So it's actually putting that carbon from the air back into the soil carbon sponge that's our key point of agency to actually restore a safe climate. The next question then comes, of course, well, how do we do that? You know, we've accepted that here's a sponge. The question is, okay, what is it and how do we actually cool that or draw that carbon back into the soil? And again, it's there that nature gives us a very, very simple, but in fact, the only option that exists to do that. And of course, that's by growing plants. And see, it's actually when plants grow, they are taking carbon from the air, they're taking CO2, they take 6 grams of CO2, 6 grams of water, sunshine to make 1 gram of sugar or cellulose. And of course, that's the process that is used to actually fix carbon. And of course, plants are doing that all the time. And basically, there's about 130 billion tons of carbon that is fixed by the Earth's vegetation every year. And so this is the process of photosynthesis. And by increasing that carbon drawdown through plants, we can actually sort of draw down carbon from the air. And then the critical thing is are we using that carbon from the plants to rebuild the Earth's soil carbon sponge? And that depends on how much of that carbon that is fixed by plants we allow to burn, oxidize back to CO2, and how much we are actually allowing or helping to get bioconverted by fungi and microbes back into the soil. So it's actually 3 steps or 3 processes, A, B, C. A is how much photosynthesis is going on the planet. We control that through farming because that's, in a sense, us growing plants. The second part of the process, B, is how much is oxidized. And again, we control that because our land, whether we're cultivating, and Didi mentioned this, whether we're over-cultivating, where we're oxidizing carbon through basically over-fertilization, biocides, fallows. See, these are all things that we control, and that governs how much of that photosynthetic carbon is going back into the air as CO2. And the other thing that we can control is how much of that carbon that's fixed by plants is actually converted into stable soil carbon through the microbes. So if we can create the right conditions in the soil for good microbial conversion of cellulose, lignin, back into stable soil carbon, we're building that sponge. So we're in control of the 3 key processes: photosynthesis, oxidation, and fungal microbial conversion of cellulose and lignin into stable soil carbon. And we control that through our farming practices. And so, in a sense, we have agency through our farming to actually regulate how much carbon is going back into the air and how much is going into our soils. I mean, obviously, it's not that we have to do all or nothing, but the point is, if we make sure that at least half the carbon that's being fixed by plant is getting converted, as in nature, into these soils, then we can rebuild the sponge and rebuild this whole hydrological cooling cycle. So that's basically the principles. Okay, basically saying here is carbon. We've got a problem. Carbon has increased in the air, the greenhouse effect. We've really made a big point. We've spent 40 years worrying about the CO2 increase and saying we've got to reduce emissions, which we must, of course. But the point is, we've just been focused on the symptom and how do we clean up the symptom. But in fact, if we look deeper down at the cause, you know, what is the actual cause? It is a lack of hydrological cooling that has actually contributed significantly to the warming. But when we look at it at that level, it also gives us agency to naturally and safely cool the planet through these hydrological processes. And those hydrological processes are all in your hands as farmers, because that's how we can actually increase transpiration, reduce the amount and the length of time that water vapor is in the air as gas, convert it into clouds, which again then cooling, reinduce rainfall from those clouds to replenish the soil carbon sponge, but also keep that surface of the soil green and protected so that it doesn't re-radiate as much heat, which is actually the engine driving the greenhouse effect in the first place. And it's really then land management practices, local land management practices, and Didi again referred to some of them, keeping the land covered all the time, things like that, that really have an enormously powerful effect in naturally safely cooling the planet. So that's the science behind it. But really the powerful thing now is to talk about where are the actual practical applications, how are people using it, what are the case studies, and really having that interactive question and answer session about, all right, how do we use this knowledge, how do we use these practices to safely, naturally cool the planet through the sponge. So I might like to sort of now stop there and then come back into that question phase to look at, okay, what are your thoughts about it, any points of detail, but also where are the applications that we're using around the world to do this.
Great, thank you, Walter. And we are getting a few questions in the chat. So I think we have a good chunk of time left to get through some of those. So the first question is, what are the steps for areas and whole countries on the planet Earth that have lost their forest cover and have become a desert environment?
Right, yeah, look, this is obviously critical, and just put it into context, there's 14 billion hectares of land on this earth, and of course that's decreasing as sea level rises. And so far over the last 8,000, 10,000 years, we've turned about 5 billion hectares, or 40% of that, into man-made desert and wasteland. Okay, so that's very, very significant. So, you know, before we had industrial agriculture, most of the planet was in fact vegetated. The Sahara Desert was a savanna, and, you know, same all over the earth. And of course, what is it we can do to reverse that? And of course, the answer very simply is rebuild the Earth's soil carbon sponge across those landscapes. Now, obviously, it's not that simple. We can't just automatically say we want a sponge, but it involves those simple steps we talked about, growing plants. So how do we basically restore pioneer plants? These are often weed plants to get stabilization and initial plant growth on those habitats. And then how do we increase through those plant growth the capacity of that soil to infiltrate, retain, and make available water, to harvest water from the air? That's another whole sort of dimension. And basically progressively recolonize those semi-arid areas, just as nature did. The point is, nature's doing this all the time. So there's a desertification process, but there's also a natural plant colonization process. And what we have to do is understand that and then redevelop and re-accelerate that colonization process. So, and then
oh, go ahead.
Yep.
I just wanted to expand on what you were saying about the plants often being seen as weeds. That it's a really key point that what can grow will grow, and that each generation of plants are they're literally creating fertile ground for the next generation of plants. So the idea of getting rid of weeds so that other plants can grow is just a flawed idea in essence. that what we need to do is to figure out ways to improve the soil, which those plants, those weedy plants, are actually the first responders, or the Band-Aids, or the scabs, or however you want to call it, that are helping to heal, helping to pump nutrients in to provide for the biology that can rebuild the sponge. So it's really learning to work along with those plants and to see them as helpers, and also to see them, as Nicole Masters says, read your weeds, that to be able to look at what's growing and say, oh, this soil must have this issue because this is growing here, rather than if I got rid of this, my soil would be better. Thanks.
Yeah, and so every plant is actually helping, because every plant that's green and fixing carbon, see, that carbon has to go somewhere. It can either oxidize or can be biosequestered into soils, and the weeds are actually doing a lot of that soil structure, soil carbon sequestration. So they're investing a lot into the soils, into their root systems. That's why they are competitive as weeds, and they are then pioneering that regeneration. And of course, we do that in agriculture, and of course, this is what the innovative agricultural, the farmers are doing. Here are cover crops. So we actually put cover crops, mixed cover crops out there to make sure that surfaces are vegetated all the time, as long as possible, growing plants, and as long as plants are growing, we're building that soil carbon sponge.
Yeah, definitely. So here in the Midwest, we have quite a few dairy farms and livestock operations. So the next question is, do you think composting of manure can be a piece of this carbon and soil health puzzle?
Look, absolutely. And I mean, see, when we're talking about rebuilding the soil carbon sponge, it's in a sense that composting process. See, compost is a process whereby organisms are taking that biomass and turning it into humus. But of course, so are animals. So then when an animal is eating pasture and biodigesting it in its rumen, it's actually a compost heap. An animal is effectively a mobile biodigester that's turning cellulose and lignin, obviously, into protein, but also then in terms of through its dung back into sort of compost materials. So we look at the agents of that biodigestion soil carbon forming process. And yes, the prairies were formed very rapidly by vast herds of herbivores, bison, turning all that grass into compost, building soil carbon, fertilizing the soil, building more grass. And when you think of it, and where you are in Wisconsin, it's only 9,000 years ago that all of Wisconsin was a glacial till. It was a mineral, waterlogged wasteland. And in 9,000 years, nature has used this grass growing and herbivore and composting process to turn Wisconsin into some of the most productive deep soil carbon areas on the planet. So, very, very rapidly, these processes have turned that mineral till in Wisconsin into highly fertile soils, and we can do that as well.
Yeah, definitely. The next question is about cover crops, and are they a good way to protect soil? They're a good way to protect soil during and after harvest, but tillage breaks apart all of that wonderful soil glue. Can covers crops help rebuild the soil sponge on their own, or is reduced tillage a must?
Okay.
I could jump in for a minute there.
Yeah, please. Yeah.
I do think that having cover crops, even if you are continuing to use tillage, has a lot of benefits in that the cover crops are feeding the soil life, and even breaking up the soil with tillage is breaking down some of that soil life, but overall it's still probably very much of a net gain over leaving the soil bare. So bare fallow is one of the worst things you can do, is both starving the soil and also leaving it out into the elements. probably a lot of the farmers on this call are familiar with it, but if you're not, I'd take a look at the work of some of the farmers that are doing grazing of cover crops, in particular Gabe Brown's book, Dirt to Soil. That is another way of dealing with having cover crops without needing to till and without using to use an herbicide to terminate.
Yep.
And
And
that
like
has a tremendous additional benefits by having the grazing in the system.
yeah. And this is where we basically have to be a bit careful. We're not being prescriptive that you must do this or you mustn't do this. Look, as long as you're growing plants, so growing cover crop is fantastic. And then the question is, yes, you've got all that carbon fixed. Now the question is, what happens to it? And obviously, if you're tilling excessively, then you're turning more and more of it back into CO2 because you're oxidizing, because you're exposing that soil to oxidation. If you don't till at all, yes, you're avoiding that. So there's a balance, isn't it? It's a case of I've got so much credit in the biomass that I've produced. And yes, if I basically need to do some tillage occasionally, but I'm not excessively oxidizing it, you're still ahead. But the point is that industrial agriculture at the moment, we're doing so much cultivation, we're doing so much fertilization, biocides, fallowing, bare fallowing, that we're in a sense turning 120% plus of the carbon that we're growing back into CO2 in the air, because we're not just turning that crop 100% back into CO2, but we're also turning residual heritage carbon from the soil from that previous 9,000 years also back into the CO2. So it's a case of what proportion of the carbon that you fixed are you actually reoxidizing. And if you can keep half of it in the soil, you're progressing. So it's not that there's a religious dogma about you must do this or mustn't do that. It's always looking at that balance. If you need to do some tillage because of, in a case, I've got to prepare a seed bed for the next crop or something, that's all okay, but it's a question always looking at that balance.
Dale's bringing up a really interesting point in the chat about the new focus on, soil carbon is kind of the media's new darling, and there's all these soil carbon markets opening up, et cetera. And as someone who was the president of the Soil Carbon Coalition, I appreciate soil carbon, and I'm excited that people are starting to see its relationship to atmospheric carbon, et cetera. But the problem is that we're still using very much of a partial view, and I would say also a kind of an extractive economic view. So soil carbon isn't just something that's on the periodic table. It's life itself. It's a reflection of life in the soil that does work. And soil carbon can't be there without water, and our climate won't function without water. Water is actually an important part of the greenhouse, and the greenhouse is part of keeping our planet warm enough for life. So this sort of good, bad, black and white, carbon in this, carbon is good or bad, or carbon is worth this much. It's not a living systems view. And
Yep.
I also see that there's a sense of like, how can we make money off of soil carbon is a way of extracting value, or how can we get rid of atmospheric carbon is like trying to stop bad things from happening. But can we take this up to a different viewpoint of like doing good in the world, or even better, regenerating life in the soil and in the planet and in the diverse landscapes, as opposed to sticking with that very partial black and white kind of profit-based mentality. Nothing wrong with profits, but it has to work as part of a whole nested system.
And look, and absolutely, and this is the whole point of the carbon accounting message that we're in, or hey, we've got to stop carbon emissions, as if carbon was some, fixed entity. Now, carbon is valuable, as we've explained, when you put it in the sponge, and because of its multiplier effect in the sponge in hydrology, when it restores the hydrology, the functioning of that soil and its cooling properties. Carbon by itself, as we've said, has a 4% effect in the greenhouse gas effect, but it's by no means able to actually resolve the problem. It's actually the resource that we need to put in the soil to build the sponge, to build the hydrology, to build these cooling processes. And just fixing on carbon accounting, you know, I've got so many tons per hectare, therefore I'm good. That won't get you there. It's basically, have I got carbon functioning biologically, hydrologically? That's where the dividends come from. And so that's that point that Didi just made to say, look, it's got to be a living, material, and it's the benefits from the carbon, not the carbon per se.
Yeah, good point. It looks like we have just a couple more questions in the chat, so maybe we'll take those before we close as we're approaching 1 o'clock. But a question came in from Aaron. It's difficult to talk about soil sponges without thinking about wetlands with their organic, material-rich anaerobic soils. Can you comment on the role of wetlands in building carbon storage in working landscapes?
Look, absolutely. And wetlands, of course, were fundamental in creating that carbon storage and, of course, the sponge. And, of course, again, in North America and Wisconsin, you had these wonderful animals called beavers that were creating these wetlands, and they would create the habitats where there was vast carbon fixation because there's very little oxidation from a wetland because most of it is turned into organic matter. And in a sense, these beavers, these wetlands were then very, very powerful sources of carbon fixation and producing very fertile soils. And of course, we came along and then we drained those wetlands and often then used those wetland soils, those beaver wetland soils, as our horticultural and agricultural prime lands, those bottomlands. And of course, in North America, yeah, I think you've used about 90 or drained about 95% of your wetlands that were there 400 years ago for agriculture. And yes, that's part of that whole process of, mining soil degradation. And we've got to now be cognizant of that and say, how do we actually restore? How do we rebuild? Not that we have to put it all back to wetlands, but those processes of limiting oxidation, that escape of carbon back to the air and keeping it in the soil. But certainly, we've got to bring more wetlands, more beavers back into the agro ecosystems that we're managing, because that's a critically important thing.
Yeah, and Walter, can you just touch briefly on the future of measuring carbon? Is that a possibility? I know you talked a bit more of a concept and things.
Okay.
Is there a way to show improvements as people make some of these changes?
Yeah, look, okay, very important. I mean, everybody, and we talked about carbon accounting, everyone's been so keen on saying, okay, how do I measure my carbon? And the real problem there comes of sampling, because this is a biologically active system and it varies enormously from place to place, how the microbiology is working. And so to get an accurate statistical measure is hard because you've got to take so many samples. That's very expensive. And the question is, can you measure it in a smarter way? And of course you can. We can look at that through its functionality, like can we actually look at soil carbon in terms of, okay, how much green vegetation it is sustaining. Okay, and so for the actual long-term global carbon accounting and measurement process, we can actually do this from satellites. We can actually monitor changes in soil carbon from space through satellites by looking at the actual longevity and intensity of green because that's basically an indirect measure of how much carbon and moisture is in the soil. So at the moment, everyone's so fixated on, can I actually measure it, you know, like through sampling and wet chemistry. In the long run, if we're going to go into carbon accounting, it can be done from space. But at the moment, what's missing is, in fact, a carbon market. You see, because why are we doing all this if there isn't actually a carbon market, a trading system that gives us value? And again, that was a challenge in the whole global COP process, the IPCC process, where we were in Paris agreed that, yes, we would have negative or zero, carbon accounting to target, you know, negative emissions. And yet we haven't fully established that global carbon accounting trading system. And until that happens, I think, yes, we can measure, but the incentive and certainly the driver behind it isn't there as it could have been.
Great. Well, thank you so much, Walter. If you're still with us, I'm going to launch a quick poll just as a quick survey to help us with our reporting. So if you could fill that out. But I would like to give a huge thank you to Walter and Didi for joining us today to kick off this webinar series. I've gotten a lot of great comments in the chat and already in my email about how wonderful it was. If you missed portions of this or would like to watch it again, we will be posting the recording on our Discovery Farms YouTube channel very soon. And it looks like Didi's shared a couple links in the chat, so feel free to visit those and check those out. But thank you again, Walter and Didi. We really appreciate your time waking up early to be with us today.
No, well, look, thank you very much, Erica. And look, thank you very much, everybody who attended. And as we sort of said, look, this is quite radical. I mean, we're really sort of getting outside the square in a significant way, particularly as far as climate change. And there'll be a lot of questions that arise. And that's really what this whole purpose is, challenge and change, right? So it all comes around, we're challenged, here are new imperatives. What are the questions? And so it's very important. Your questions are really the critical thing, because that's how you're basically saying, okay, look, how do I take this information? How do I use this information? What are the options I've got for now taking this forward? And so please feedback all those questions. And then we're very, very happy, obviously, to answer them. And then also to say, look, where are there further areas where we need to have more discussions and exploring these solutions? But that interaction of your questions and our basically capacity to answer them as best we can is really where progress is made. So thank you very much. And we just encourage more of those critical questionings and examinations.
Great. Thank you so
Thanks
much.
again. Thanks again for having us. Great.
Thank you very much.
Really interesting questions that came up in the chat there.
Yeah, and a reminder to tune in next week. We will be joined by Amber Raditz, co-director of the Discovery Farms program in Wisconsin, as well as two farmers, Rick Adamski and Brock Olson. So tune in next week, and I'm going to end the recording now. So thanks, everyone.
Okay, thank you very much. Bye-bye.